So I'll be talking about joint work with Yu Deng from Chicago and Xiao Ma from Michigan. So Hilbert's sixth problem was one of the problems that Hilbert suggested in the 1900 ICM, and it asks for the axiomatic derivation of the laws of physics. So basically what we'd like to do is that we'd like to take some fundamental laws of physics or first principles. We want to take those as axioms, mathematical axioms, and try to derive with mathematical rigor using only mathematical logic other laws of physics, particularly, for example, laws of statistical physics. And of course, broadly interpreted, the scope of this problem encompasses all of modern mathematical physics. Perhaps realizing that in his follow-up paper, Hilbert, where he expanded and explained his problems, Hilbert specified two concrete questions under this sixth problem. The first one was giving the rigorous mathematical foundations of probability theory. This was something that was done in the first half of the past century. And the second question concerns Boltzmann's kinetic theory, which will be our subject of interest today. So in this regard, he says, Boltzmann's work on the principles of mechanics suggests the problem of developing mathematically the limiting processes there merely indicated, which lead from the atomic view to the laws of motion of continuum. Okay, so this is what we're going to try to understand. We will try to understand how to go from the atomic view of matter to the laws of motion of continuum. And what does this mean? It means basically justifying this diagram over here. So what we want to do is that we want to justify rigorously the following two limits. We want to start with Newton's laws on a group of n colliding particles. This will be our microscopic system. We want to take a first limit, which is the limit that Boltzmann took, in order to go from this microscopic description to an intermediate scale that is called a mesoscopic scale, where Boltzmann's kinetic theory lives. And then we want to take another limit, which is called the hydrodynamic limit, which links Boltzmann's kinetic theory, or this mesoscopic scale, to the macroscopic scale, which is given by hydrodynamic equations. These are the equations of fluid mechanics that we use in everyday life, like Euler's equations and Navier-Stokes equations. The last scale, as I said, is the macroscopic scale. This is a picture of Newton, Boltzmann, and Euler over there. So performing those two limits in tandem and rigorously is what is called Hilbert's program. And what is really fascinating about this program, both from a philosophical and also mathematical point of view, is that it features a passage from a system that is reversible in time. If you watch a video of gas particles in this room, there's no way for you to know whether the video is going forward or backwards in time. This is a reflection of the fact that Newton's laws are time reversible, whereas, as we all know, the laws of statistical physics are irreversible. Boltzmann's kinetic equation features an entropy that increases in a specific direction of time. So part of understanding this passage is part of understanding the creation of this arrow of time. The second limit, which is going from Boltzmann's kinetic theory to the hydrodynamic equations, this limit has been well understood for a while now, even since the past century. This is starting with works of Nishida, Kaflish, and others. And so I will not elaborate at all about this hydrodynamic limit. It's safe to say that it's very well understood. And the main difficulty is really in justifying the first limit, going from Newton to Boltzmann. So let's review quickly Boltzmann's kinetic theory. This was proposed in 1872 by Boltzmann. And the idea there is that we want to start with n particles that are obeying Newton's laws. Each of those particles has a diameter epsilon, and they are undergoing elastic collisions. Okay? And the vision of Boltzmann is, rather than try to, if I want to understand the gas dynamics in this room, I'd rather not solve an Avogadro's number of ODEs in order to understand the trajectory of each of those gas particles. Instead, we would like to take a statistical description of the system and try to understand the effective dynamics, for example, of the density of the particles. So this one-point density, f of txv, so the probability of finding a particle at position x and moving at velocity v at time t. Okay? So the microscopic system, or the microscopic description, is given by Newton's laws. So these are just quite elementary. So the first point is that if the distance between the centers of any two particles I and j is greater than epsilon, or then the particle I will just go in a straight line. If it's not colliding with any other particle, it will go in a straight line. This is Newton's first law. But if it gets to a situation where the distance between particle I and particle j is exactly equal to epsilon, in other words, if the particles are colliding, then they exchange velocities in the following way. So if particle I comes in with an ingoing velocity VIN and particle j comes in with an ingoing velocity VJN, then the outgoing velocities are related to the ingoing velocities by those equations. And we've all seen those equations in high school physics. They are just consequences of conservation of momentum and conservation of energy upon an elastic collision. Omega is the unit vector pointing from the centers of the two particles. And up to technical manipulations, this is a time-reversible, volume-preserving dynamical system. So like Boltzmann, as we said, we want to take a statistical point of view. So we're going to think of the initial data for the system to be distributed in a random way. So we'll think of at time t equals to 0, the particles are distributed randomly and independently with a one-point density function f initial of z. I'll explain what this means in a minute. So for the rest of this talk, we'll use this shorthand notation and use z to denote a position velocity vector. So x is in RD, v is in RD, so the position velocity vector is z, and the one-point density function at time t equals 0 is f initial of z. This you can think of it as at time t equals to 0, what is the probability of finding a particle at position x moving at velocity v? And what we mean by the system being in an independent state at time t equals to 0, we mean that if I look at the endpoint density function, this is the probability of finding particle 1 at position velocity z1, particle 2 at position velocity z2, up to particle n at position velocity zn, then this is given in a factorized state as follows. So this is, the important thing here is what is in red, that this is an s-fold product of the one-point density function. This is a reflection of the independence between the particles. 1 over zn is just a normalization factor. And of course, we will also multiply by the characteristic function of the domain of propagation. And the domain of propagation is just the statement that the distance between any two centers of the particles is always greater than or equal to epsilon. Okay, so this is the initial data for the system. This is once I specify the initial data for the endpoint density system, endpoint density, then I get a deterministic system and for the densities at least. Okay, and Boltzmann's theory or this kinetic theory will appear in a limit when I take the number of particles to infinity and the diameter of those particles going to 0. This is where we start seeing statistical physics. Those two limits cannot be taken arbitrarily, and it took some time to understand that we really cannot take those two limits arbitrarily. They have to be taken in such a way that n goes to infinity and epsilon goes to 0, such that n times epsilon to d minus 1, this is called the collision rate, is order of 1. This is something that was discovered by Grad around 1950s. Or the necessity of this condition was discovered by Grad in the 1950s. And roughly speaking, it says that in time order of 1, you would have an order 1 of collisions happening. Okay, this is a statement about the diluteness of the gas. Okay, and it is necessary in order to observe Boltzmann's theory. Okay, so what does Boltzmann's theory tell us? It tells us the following. So remember, at time t equals to 0, I took the particles to be independent of each other. Okay, now as I turn the interaction on and I start seeing the video of the particles colliding, the particles, by the fact that they are colliding, they will start building correlations between themselves. So this factorization will break at the macroscopic level the minute I let time to be greater or equal to 0. But kinetic theory and Boltzmann's kinetic theory all hinges on this observation, ingenious observation of Boltzmann, which is now we call it propagation of chaos or Boltzmann's molecular chaos assumption. And what it says is that this factorization, while it breaks at the microscopic scale, it is retained at the mesoscopic scale. In other words, if I take the limit as n goes to infinity first, then this factorization is preserved. Okay? So this is what we call propagation of chaos, and it's really at the heart of Boltzmann's theory. And what this means that at the mesoscopic scale, at this intermediate scale, if I look at the s-point density function, then this is just a product of one-point density function. This is independence at the mesoscopic scale. In other words, Boltzmann's tell me that the only thing that I need to track is the behavior of the one-point density function. And this is the other component of Boltzmann's theory. This is Boltzmann's celebrated kinetic equation that tells us the effective dynamics of the one-point density function at the mesoscopic scale. And this is given by what we call now Boltzmann's equation. It is written over here. On the left-hand side, there's a transport term, dt plus v dot grad f. And on the left-hand side is the collision kernel. This is q of ff. The initial data at time t equal to 0 of this PDE, you take it to be the same initial data for your one-point density function of the particle system. Okay, and this is the collision kernel. I won't spend much time explaining what it says. Just maybe explaining notation. It's an integral over Rd and Sd minus 1. Omega is in Sd minus 1. V1 is in Rd. And here the point is that we use the notation that V and V1 are incoming velocities and V prime and V1 prime are the outgoing velocities upon a collision. So when we write F prime here and F1 prime, we mean F at x V prime and F1 prime is F at x V1 prime, etc. Okay, this is called the collision kernel. Okay, so here's the timeline of, and some literature on the matter. Of course, Boltzmann suggested his theory in 1872 and derived this kinetic equation assuming the molecular chaos assumption. Then in 1900, Hilbert proposed the rigorous derivation of Boltzmann's equation as a way to get to the rigorous derivation of the fluid equations. This was the ultimate goal of Hilbert, to get into a rigorous derivation of the macroscopic laws of fluid dynamics. Then there has been a lot of work that I only select a few of it here in the past century. Grad and Cercignani around the 1950s, or between 1950s to 1970s, worked a lot on this problem. And for example, as we said, Grad introduced this Boltzmann-Grad scaling that is needed in order to rigorously derive Boltzmann's equation. Cercignani introduced a BBGKY approach to the derivation. This is, as many of you know, this is Birkwood, Born, Green, Bogoliubov, Born, Green, Kirkwood, and Devon. And so this is an approach, a hierarchical approach to give a derivation of Boltzmann's equation. And this is the approach that Lanford did to give it. This was the biggest landmark result in the past century on this problem, on Hilbert's sixth problem, which is this work of Lanford in 1975. And what Lanford did is that he used this BBGKY approach in order to give the first rigorous derivation of Boltzmann's equation. So what do we mean by rigorous derivation? We mean that if I look at the one-point density function of the particle system, again, the probability that I find a particle moving at position x, at position x moving at velocity v, then this is something that converges to the solution of Boltzmann's equation. In the limit as n goes to infinity and epsilon going to 0, again, under the Boltzmann-Grad scaling law. Now, the main caveat of this result is that it only held for short times. And we will see why this short-time restriction was necessary. So he was able to give a derivation of Boltzmann's equation for times that are much smaller than 1. Okay. Then the progress continued after that. In the 80s, Euler and Pulvirenti gave a long-time derivation of Boltzmann's equation, but under an equally big caveat, which is the near vacuum case. So this is equivalent to assuming that you are starting with small initial data for the Boltzmann equation. Then there was work also in the 90s by Pulvirenti and collaborators, Olla Varadaniao, Riza Kanlu, who observed that those questions become much more tractable if you introduce some stochastic element to your microscopic system. So they derived kinetic and hydrodynamic limits for stochastic particle models that were introduced. Then the theory was revitalized around 2010, starting with the work of Gallagher, Saint-Raymond, and Texier, who revisited Lanford's proof and even proved explicit convergence results. Along the same time, Pulvirenti and Suminella revisited the problem as well and studied cumulants, which will be important things for us later in the talk. Also from 2016 to 2018, Bodino, Gallagher, and Saint-Raymond studied some linearized models, macroscopic limits. These are based off linearized Boltzmann's equation, in other words, starting at equilibrium, some sort of equilibrium for your particle system. And then from 2018 to 2024, the same group with Simonella studied fluctuations and large deviations about this Boltzmann limit. So in other words, you understand this Boltzmann limit as a first order limit, and then you try to understand what is the second order corrections. In other words, and more precisely, you really should understand this Boltzmann limit as a law of large numbers, and then the question that one can ask is, what is the corresponding central limit theorem that appears there? And again, they studied those questions either under the short time restriction like Lanford or in linearized settings. So as we said, as was obvious in the description, all the above results were either restricted to short times or near vacuum settings or linearized settings, okay? In particular, this does not allow us to link those two limits that were on the second slide, the kinetic limit and the hydrodynamic limits, okay? So we really, those kind of results are not enough to take those two limits in tandem. And the reason for that is that the hydrodynamic limit itself is based on getting access to solutions of Boltzmann's equation that are large and exist on long time intervals, okay? And this brings us to the main question that remained open for a very long time, whether we can give a derivation of Boltzmann's equation from the hard sphere particle system for long enough time intervals. How long? At least as long as the solution of Boltzmann's equation exists. Okay, and in short, this is equivalent to giving a long time extension to Lanford's theorem. And this is the main result of this talk. Okay, so this is, as I said, joint work with Yu Deng and Xiao Ma on two manuscripts in 2024, and one in August 2024 and the other in March of this year. So we consider a hard sphere system in any dimension d greater than or equal to 2 under the Boltzmann-Grad scaling. And we suppose that we have a solution to the Boltzmann equation that exists on some time interval 0 t final. And the key point here is that this t final could be arbitrarily large, okay? Then for any fixed s and any time between 0 and t final, we have the following statement. If I look at the s point joint density of the particle system, this is again the probability of finding s particles at positions, velocities z1, z2 up to zs, then this is something that is well approximated by the s-fold product of the solution of Boltzmann's equation. So if s is equal to 1, this is the statement that the one-point density function converges to the solution of Boltzmann's equation, and the convergence is in a strong norm, L1 norm.
Do you know how far it goes to
Yeah,
0?
we have an estimate on if epsilon is the radius of the particles, then this difference goes like epsilon to the nu. So it's small power of epsilon, or small power of n, 1 over n. Yeah. Okay. So there are just some technical remarks about the result. The regularity assumptions on the Boltzmann solution are basically the same as in Lanford's classical theorem. You assume that the solution exists, it's L1 in X and Maxwellian weighted in V. The theorem that I told you about holds both on RD, this was the paper from last summer, and on the compact domain, the torus, in which case the dimension is either 2 or 3. This was the result from this March. And these are exactly the kind of long-time results that we need in order to link the kinetic limit and the hydrodynamic limit. Okay, so these long results can be combined readily, essentially as black boxes, with the works that justify the passage from Boltzmann's kinetic theory to the equations of hydrodynamics. Okay, and thus fully executing Hilbert's program in this Boltzmann-Grad limit. So this is a sample of such results from our paper in March. So suppose we consider the hard sphere system in dimension d greater than or equal to 2. Actually, maybe d 2 and 3 here. There's a typo here. Under the Boltzmann-Grad limit, so we assume that there's parameter alpha, which is, as I told you, the collision rate. That sort of can think of it as the number of collisions that are happening in unit time. Okay, and this is the parameter alpha that needs to go to infinity in the hydrodynamic limit. And then we consider a solution of compressible Euler equation This is one of the hydrodynamic models that we'd like to derive on an arbitrary long time interval, 0t final. Once we have a solution of compressible Euler, I form what is called the local Maxwellian that is corresponding to this solution. So rho is the density, t is the temperature, u is the fluid velocity. Then what we can say is that if I look at the one-point density function of the particle system, then this is well approximated by this local Maxwellian in the limit, okay, in the limit in the kinetic limit. And a similar result can be formulated for other fluid equations like incompressible Navier-Stokes. Okay. Before I start telling you about the proof, I want to say that we sort of arrived at this problem in a somewhat funny way. Or at least my initial starting point was to study a wave counterpart of Boltzmann's theory. Okay, so this goes by the name of wave kinetic theory or wave turbulence theory. Okay, so this is, so here, strictly speaking, what you do is that you replace colliding particles by interacting waves. And so instead of thinking of particles colliding and interacting with each other, you think of waves interacting with each other, like waves in the ocean, for example. And instead of Newton's laws that tell you how the particles interact at the microscopic scale, you have another Hamiltonian system that tells you how waves interact at the microscopic scale. And this is typically given to you by some wave type, PDE, or even an ODE, like coupled harmonic oscillators, for example. So, for example, in the most fundamental setting or most universal setting of the nonlinear Schrodinger equation, so this would be our microscopic system, the waves would be interacting according to this PDE that is written over here. So there, on the right-hand side is the Schrodinger equation, and on the left-hand side is the nonlinearity, a cubic nonlinearity. We pose this equation on a large box of size L, with periodic boundary conditions. So L would be the parameter that reflects or mirrors the number of particles in the Boltzmann's theory. So L will be going to infinity. And alpha, this is the parameter signaling the strength of the nonlinearity. This is the parameter that mirrors the size of the particles. So this is the parameter that will go to 0 in the kinetic limit. And in an appropriate kinetic limit, we get a kinetic equation. This is the wave analog of Boltzmann's equation that is written over here. So in a homogeneous setting where you don't have space dependence, you only have dTf on the left-hand side. In an inhomogeneous setting, you have dTf plus v dot grad. And the collision kernel even looks a lot like the Boltzmann collision kernel, except that the interaction now is cubic rather than being quadratic. Okay? Last slide. Yeah, we'll discuss that. F1, yes. Again, this is the shorthand notation that I told about. So you think of, this is V1. These are colliding, and the outgoing velocities are V prime and V1 prime. And then F1 is a shorthand for F of T V1. And F1 prime would be F of T V1 prime for you, etc. F prime would be F of T V prime. Yeah. So these are just shorthands, common shorthands in kinetic theory for, so this would be F of a T x V prime, okay? And V prime would be, oops, that's not it. V prime is related to V by the same conditions that I wrote on the second slide. Basically, prime is V minus V1 dot omega. Okay. Okay. So unlike the particle theory, this theory was, the mathematical study of this theory is much more recent, and we actually started it in the past 10 years or so. So following some foundational works that I will not mention all the authors, but part of it was with Jalal and part of the Simon's collaboration grant. In a series of joint works with Yu Deng in 2021 and 2023, we gave the rigorous foundations of this theory in the homogeneous setting, including proving the analog of Lanford's landmark theorem in the particle case. So remember, Lanford's theorem in the particle setting was the derivation of the kinetic equation for short time. So this was the first step. It took us quite a bit of effort in order to get to this short time derivation of the wave kinetic theory. And then in 2023, we succeeded in extending this derivation to longer times. So what we gave in 2023, we gave the justification of wave turbulence theory and the derivation of the wave kinetic equation for arbitrary long times. And this was the very first result of its kind. This was the first time where we were able to give a rigorous derivation of a collisional kinetic theory for long times. And this is what gave us the hope and even the strategy in order to attack the classical problem raised in Hilbert's sixth problem, which is the derivation of Boltzmann's equation. Yes, there's no x dependence. Yeah. So basically, you take a random field of initial data that is translation invariant. Yeah. So the two proofs in the wave setting and in the particle setting, they're conceptually the same, and they follow the exact same framework and methodology. In fact, everything that I will tell you about the particle proof today extends, has an exact analog in the wave setting. Okay, so but I will use the particle theory because particle theory in order to illustrate and elucidate the ideas of the proof. Okay, so this is what we'll move on to next. So all those proofs are based on, we really have one approach to give such proofs, which is based on diagrammatic expansions. So, or this is like expansion into Feynman diagrams. So what this means is that what you do is that you take you do a time series expansion of all the solutions involved. Okay, so maybe again, I like to use this diagrammatic. So we have two solutions here. We have a solution of the microscopic system, which is very complicated, the particle system, and the solution of the kinetic equation. So what we do is that we do an expansion of both solutions in terms of diagrams. So expansion of microscopic system. And then there's a considerably less complicated expansion of the kinetic equation that we want to prove that it is the limiting equation, which is Boltzmann equation. Okay? And one of the first steps of the proof, actually one of the first things that you need to understand is to identify the leading order diagrams here. Okay? Think of those expansions as being Taylor series expansions. They are really Taylor series expansions. Think of them as power series expansion. And what you want to do is that you want to identify the leading order diagrams here and show that they converge order by order to the expansion of the kinetic equation. Then the bulk of the work goes to showing that everything else goes to zero in the kinetic limit. Yeah. Yes, trees, you mean. Trees, yes, you can, definitely, yeah. So this is the sort of the caricature of the proof that is involved, okay? So this is, we already mentioned that. And the way you show that these series converge is by showing an upper bound of those series of the form, they are bounded as sum from k equals 0 to infinity of c to the k, t to the k. So you show power series upper bounds of them. And this is, you directly see why you need this short time restriction, or why Lanford needed this short time restriction, because power series only converge in the radius of conversion. So here you need, this only converges when t is less than 1 over c. Okay? So this is why the short time restriction of Lanford was really a fundamental restriction. And this tells us what the main challenge is in order to extend this result to longer times. The challenge is that all those diagrammatic expansions diverge when time is large. okay? Just like you're think of the function 1 over 1 plus t. This has a power series convergence at 0 of sum of minus 1 to the n, t to the n. This diverges at t equals to 10. So what do we do about that? So the first idea to resolve those difficulties is a rather simple idea, which is that of time layering. And this is the idea that is needed in order to resolve the divergence issue for the simpler expansion, which is the expansion of the Boltzmann equation over here. So for this simpler expansion, there's an easy way to resolve the divergence problem, which is time layering. So what we do is simply split the time interval 0 t final into time layers, L tau, L plus 1 tau, such that we can pick tau small enough in such a way that the Boltzmann solution, the solution of the Boltzmann equation, admits a time series expansion, but only on each time interval L tau, L plus 1 tau, with base point L tau. So think of like for the function 1 over 1 plus t, the analytic function 1 over 1 plus t, you split the interval 0, 10 into subintervals, such that on each of those subintervals, you have a convergent power series expansion, but the base point is different, okay? So while this resolved the divergence issue of the Boltzmann equation or of the kinetic equation, it really does nothing to resolve the divergence issue for the more complicated expansion, which is that of the microscopic system or the particle system. Okay, again here, so what we're doing is we split this time interval 0 t final into layers tau, L tau, sorry, 2 tau, etc. Okay? And the reason why it does nothing to resolve the divergence issue of the expansion of the microscopic system is that even going to the time tau, 0 tau, this is Lanford's result. And I can promise you this is a very involved proof. And the only reason why we can show that the Feynman diagram expansion of the particle system converges on this very short time interval 0 tau is because we assume that at time t equals to 0, the particle system was in a factorized state. So we had perfect factorization. In other words, we assume that at time t equals to 0, the particles were independent of each other. And of course, in the time interval 0 tau, many particle collisions have happened, and we do not have factorization at time t equals to tau. Okay, so there's a natural obstruction why we really cannot repeat Lanford's proof as it is. Okay, but this also gives us the idea of what is needed in order to go for longer times. What is needed in order to go for longer times is that I need to understand how much did I lose of this independence that was at time t equals to 0. Okay, so at time t equals 0, I had perfect factorization. The particles were independent of each other. Now I need to understand how much did I lose of that as time goes by. And there is an object in statistical physics that exactly measures that. This object is called cumulants. It really measures the failure of independence at later times. Okay. So the exact definition of the cumulants, I won't give it here because it's a bit technical. But what is really important is this expansion. And this will be the only formula in this talk. So let's try to read this very slowly. So the left-hand side is the S-point density function of the particle system. Okay, this is the probability of finding particles, S particles, 1 up to S, at position Z1 up to ZS. Okay, so ZS here is a ZS over here is, I don't know if I can use a pointer. Yes, this is a vector Z1 up to ZS, okay? Now, on the right-hand side, I have the main term, or the leading term, is the S-fold product of a function G, okay, which I can think of it as the one-point density function. So this is the factorized part of the S-point density function, okay? Then comes the cumulant contribution. Okay, so if it weren't for the second part on the right-hand side, factorization is actually retained, but we know that it is not. So we have correction to this perfect factorization, which is given by the cumulants over there. So, and it turns out that one can show that they enter in the following fashion. So we can write the correction to perfect factorization as a sum over all subsets of the set S, this is the set 1 to S, of a factorized part, which is the particles that are not in this set H, and a cumulant part, E sub H. So this E sub H are what we will call the cumulants. Okay? And the only thing that you need to keep in mind about those E sub H, or those cumulants, is that it signifies the fact that if it's not zero, then this signifies a state where the particles in H have built some correlation amongst themselves in the time interval 0 L tau. Okay? The particles not independent, so they have built correlation between themselves, and mainly through collisions. Okay? So here's a heuristic of this expansion. Why do we expect this to hold? So in the case S equals to 3, suppose I'm looking at the 3-point density function. This can be written as a sum over the collision histories that are involving those 3 particles, 1, 2, and 3. So I have 3 particles, 1, 2, and 3. And if I look at the F3 of Z1, Z2, and Z3, this is something that I can expand using cluster expansions, for example, in terms of as a sum of collision histories of those 3 particles. And this is, and then what you do is that you classify those collision histories, and after this classification, you end up with this formula. So here's an example of a collision history. I have the 3 particles 1, 2, and 3 at time tau. In the interval 0 tau, what happened? Particle 1 collided with particle 4. Particle 4 before that collided with particle 2. So particles 1 and 2 got correlated to each other by collisions in this time interval. On the other hand, particle 3 collided with particle 6, and before that it collided with particle 5. In particular, it had nothing to do with particles 1 and 2. So this kind of collision history will feed into the part of the expansion that is given by G of Z3. So Z3 is really state independent of the others, and then the cumulant part will involve the particles 1 and 2. Okay, so this is the heuristic of why the expansion on the previous slide comes up. The exact proof involves, as I said, using cluster expansion. So clusters are a group of particles that are connected by collisions. So clearly 1, 2, and 4 form a cluster here. 3, 5, and 6 form a cluster. And so you do cluster expansions in each layer, and then you do an induction on layers, and then there's a very crucial new idea that is I don't think I'll spend so much time explaining what we call partial time series expansion that is needed in order to avoid divergence in this diagrammatic expansion of the microscopic system. So at this level, the upshot is that now we have a good diagrammatic expansion and Feynman diagrams of the microscopic system and the limiting system, which is the kinetic equation that holds over very long time intervals. And we have this formula that we discussed on the previous slide. But this formula tells us exactly what we need to do to prove our theorem. Remember, our theorem is stating that the S-point density function is to be approximated by the S-fold product of the solution of Boltzmann's equation. And this is achieved if I can show that G of L tau is very close to the solution of Boltzmann's equation, and if I can show that those contribution of the cumulants is lower order in the limit. Okay? So the main goal now becomes to show the smallness of those cumulants, say showing that the cumulants are less than epsilon to some power. Okay? And of course, the approximation of G to the solution of Boltzmann equation, but this is something that is, I will not discuss it. It's less important. Okay, so for the rest of the talk, we'll discuss why the contribution of the cumulants is small. Okay, so now we get to some explicit diagrammatic expansions. So it turns out that the cumulants, we can expand them as follows. We can expand them in terms of diagrams. And the Feynman diagrams in this setting, we call them collision history molecules. Okay, so if I look at the L1 norm of the cumulants, I can write that as a sum over diagrams. These diagrams will be the CH molecules of a quantity I of M. Okay? So let's understand what's involved here. So those CH molecules are nothing but graphical representation of the collision histories of the particles inside H. Remember, the only thing that I ask you to remember about this cumulant E sub h is that the particles inside H have been correlated to each other in this time interval 0 L tau, okay? So I look at all possible trajectories, all possible collision histories that lead to those correlations between the particles in H, okay? And the way I form those diagrams that we call molecules is as follows. So I look at one such trajectory. All we do is that whenever two particles collide, I form a graph that replaces this collision by a node. And then the linear motion of the particles between two collisions is replaced by an edge. Okay, so I abstract it and I get a graph out of this collision history. So these are the collision history molecules. And then I of m is just an integral expression that tells us the probability that this collision history happens. So if I tell you that particle 1 collides with particle 2, and before that it collided with particle 3, I of m tells you what is the probability of this happening. Okay, and it's an integral expression. And this brings us to the central concept in this business, which is that of recollisions. Recollisions can be defined as loops in these diagrams that we talked about before. Okay, so these are graphs. If I consider them as undirected graphs, I can think of cycles in this graph or loops in this graph, and this is what we will define as collisions. This is a statement. For example, this green particle over here collided with the red particle. Then the red particle collided with the blue particle, and then the red particle and the green particle met before that and collided before that. So I'm going backwards in time here. Okay, and this is what we will call a recollision. Okay, why are those important? They're important because, again, I go back to this expansion, this diagrammatic expansion of the cumulants. Recollisions cause a divergence in this sum over here. In other words, if I allow this M to have more recollisions, then I have much more elements in this sum. The number of elements, the number of diagrams in this sum diverges. But if you believe the result to be true, this divergence in the number of diagrams has to be balanced by a gain in I of M. So what we expect is that if a diagram has more recollisions, then this diagram has to be less likely to happen. Okay? And quantifying this intuition is the heart of the proof. Okay? So this is what we will really try to do, is quantify precisely how much do we gain in I of M as the number of recollisions in the inside M increases. And the way we do that is by a process that is called cutting. Okay? So this is what we will do, is that we'll start with a collision history diagram, which, by the way, could be almost arbitrarily complex. Then we'll start cutting this diagram in such a way that every time I get less and less complex diagrams until I cut it in such a way that I'm left with pieces that are small enough that I can compute their probabilities by hand. Okay? And how does this cutting happen? So here I'm cutting in this diagram. I'm cutting this diagram over here, and I'm getting two diagrams, M1 and M2. There's only one rule to this cutting, one important rule to this cutting, which is the following, that if you cut an edge of the diagram over here, so if this is a pair of scissors, then you get two ends. What you have to do is that you have to specify one of those ends to be fixed, okay, and the other one to be free. The reason for this is nothing but Fubini's theorem. So in Fubini's theorem, if you're integrating f of x1, g of x1, x2, and in the expression of I of m is an integral expression, so it has things like that. This is a caricature, of course. Then what you do is that you first integrate in x2, so g of x1, x2, dx2, while holding x1 fixed. This corresponds to this part of the graph. So you fix x1 and integrate x2, and then you integrate in x1. Okay, so really the fact that you have to assign one of them to be fixed, one of them to be free is just Fubini's theorem. And then again by Fubini's theorem, you get that if I cut a diagram M into two diagrams, M1 and M2, then the probability of the bigger diagram is bounded roughly speaking, by the probability of the smaller ones. And this is just comes from, because I can bound this by f of x1 dx1 times the maximum in x2, or maximum in x1, of the integral of g of x1 x2 dx2. Okay, so this, you can think of it as I of m2. This is I of m1. Okay, so this is the basic reduction process that we use in order to estimate the probability of a very complex collision history diagram. And this gives us the strategy how to proceed. The idea is to cut this M into elementary components mk. So I will keep on cutting until all that I'm left with are molecules that are so small that I can estimate their probabilities by hand. Okay? So, and how small they involve means that they involve 1 or 2 atoms or 1 or 2 collisions. Okay? And if I do that, then the estimate on I of m is roughly speaking just the product is bounded by the product of I of mk. Okay? So let me tell you a little bit about those elementary components and their estimates. So the most elementary molecule is the one that you see here. Okay? So this is, we call it a 3 molecule because it involves one node of degree 3. So a fixed when an edge that is connected to a node is fixed, we don't count it to the degree. So this has a 3 molecule. And this corresponds precisely to this following billiard shot. Okay, so in billiard you want to shoot, of course, the white ball to hit the red ball, and then the fixed end in this molecule corresponds to the statement that I want the ending destination of the red ball to be in that pocket. Okay? And the probability of making this shot, if you're dealing with particles of diameter epsilon, is really order of epsilon to the d minus 1. Because if you average over all initial configurations, what you have to do is that you have to really angle this shot in a window of size epsilon in SD minus 1, and the measure of a window of size epsilon in the unit sphere is epsilon to the d minus 1. Okay? So this is the most important example of a 3 molecule, of a elementary molecule. Okay? The second most important example is this elementary molecule that involves 2 atoms, okay, or involving 2 collisions. Okay? So we call this 3-3 molecules because there are 2 atoms, and each of those atoms have degree 3, because each of those atoms have one end that is fixed. And there's also a nice picture of a billiard shot that corresponds exactly to this 3-3 molecule, which is the following. So this is a much more complicated billiard shot. You have 2 red balls now, and you want to hit the first red ball and put it in this pocket, okay? And then you want the white ball to keep on going and hit the second red ball and put it in this pocket over here. Of course, this is a much more elaborate shot, and this is translated by the fact that the probability of making this shot is much smaller. And we can compute the probability of making this shot. This is, again, something that is, okay, it's maybe 3 pages of computations, but it's something we can do by hand. And we have a gain. It features a gain. So the probability of this shot is epsilon to d minus 1. So if it was just that, then there's no gain. It would be the same as the previous slide. But we actually do have a gain that can be, I mean, 1/2 is enough, but it's actually more than 1/2. Okay, so what this means is that the probability of this shot is this much, and this will be the smallest unit of gain for us. Remember, the idea is that what we're doing is that we are cutting an arbitrarily big molecule into small enough pieces, and these are the pieces that show up. Okay? So if I have a gain in such pieces, it means that I need to maximize the number of such pieces in my cutting. Okay, so this brings us to the purely combinatorial part of the argument. So the estimate on I of m reduces to a cutting algorithm where we want to cut our initial collision history diagram into pieces in such a way that we maximize the number of good elementary molecules. We want to maximize the number of those 3-3 molecules, okay, and minimize the number of lossy molecules. There are lossy molecules that I didn't tell you about, But so you want to minimize those diagrams that appear, okay? And the rough idea, why this makes sense, is that the rough idea is that many recollisions means that you have to make many of those 2 pocket shots on the previous slide, okay? So if you have many recollisions, you should, things, roughly speaking, for a good proportion of recollisions, you should see an elementary molecule like this 3,3 molecule. And one can see that a little bit over here, even in this very trivial example of a recollision. So in this trivial this very simple example of recollision, where the recollision only involved 3 particles, and it was only involved a triangle in this diagram, if I do the cutting over here, notice that what I get is exactly a 3,3 molecule. So the appearance of those 3,3 molecules is very much intimately tied to the number of recollisions. I should point out here is that what the diagrams that I'm drawing are very much oversimplified. The loop over here could be a loop that involves many particles, and it could be a much bigger loop. So the actual proof is considerably, of course, more involved than what I described, okay? So the algorithm has to guarantee that the number of 3,3 elementary molecules minus the number of lossy molecules is comparable to the number of recollisions. And once I have that, I would have gotten a gain in my estimate on I of m. I of m was the probability of this collision history that carries inside it gains that are comparable to the number of recollisions, okay? So which means that if I go back to this equality up there, then even though this sum diverges with the number of recollisions, we can quantify exactly how it diverges, then I still have a gain in I of m as the number of recollisions increases, and this gain will be enough to offset this divergence. Okay? This is based on a rather complex combinatorial argument. This is what we call the cutting algorithm, and it's probably the most technical part of the proof. Of course, in the wave case, remember we had a wave proof that preceded this proof. We also had a cutting algorithm over there. Somehow it was more complicated in the particle setting. The analytical part of the proof was more complicated in the wave setting, but the combinatorial part was more complicated in the particle setting. Okay, so maybe I'll finish my talk with discussing some future horizons, what really comes after this. Okay, so the first, or one of the first things that we'd like to see, and we hope that this is now an open avenue of investigation, is the following. First, we would like to consider other microscopic interactions. What I told you about now is just particles modeled like billiard balls colliding with each other elastically, okay? We would like to understand what happens in the case when the particle interactions are a bit more complicated, like if there's a potential interaction between the particles, like over here. Okay, so phi is a suitable potential function. Okay, so this for short times and for potentials phi that are compactly supported, so these are very short range potentials, we have a short time theory. Okay, this was done by King in '75. King is a student of Lanford at Berkeley, and then this was revisited, and some gaps were filled by Gallagher, Saint-Raymond, Texier, and independently by Pulverenti, Safiro, and Simonella in 2014. Okay, so getting to long times for such problems is very important. Not only getting to long times, but also maybe trying to get to deal with interaction potentials that are not compactly supported. This is still open even for short times. Then there's the question that was asked earlier, which is the quantum setting. What happens if I change Newtonian interactions between the particles into a quantum interaction? So I replace Newton's laws by the n-body Schrodinger equation. And there is a quantum analog of this theory that was laid out in the early 20th century. This is called quantum Boltzmann's equation. And this equation is still not rigorously derived even for short times. This is something that we're working on, and we hope to be able to say something in the near future about it. And this problem is, I'm quite fond of this problem because for several reasons. First, it's really a combination of the wave and the particle kinetic theories, given that quantum theory features particle-wave duality. From a mathematical point of view, it involves very interesting new techniques that we are learning, like non-commutative probability and free probability gets into this. And even this is something that, from a physical point of view, this is something that is important in superfluidity and even maybe for quantum computing. So this is a really fascinating problems on so many fronts. The other question that we'd like to understand is what happens for other scaling laws. All what I told you about, deriving the macroscopic fluid equations using Boltzmann's theory as an intermediate step, really led us to restrict to a dilute gas regime. This is the Boltzmann-Grad limit, okay? What happens if I'm dealing with a gas that is not very dilute? So in that setting, I don't have this intermediate step. It's really like you're trying to cross a river, and we were lucky enough that we had Boltzmann's theory as a sort of small island in this river that we jumped on it in order to cross it. But once we are dealing with gases that are more dense, we lose this intermediate island, okay? So what happens when it comes to the question of deriving fluid equations for more dense gases? Related to this problem is the derivation of another fundamental kinetic equation, which is Landau's equation, which also deals with a gas that is more dense than in a dilute gas, but the interactions are rescaled. And this is still open even for short times. And finally, there's the question that is even more open-ended, is what about how does this help us in understanding singularities of fluid equations? We know that some of those fluid equations at the end, like compressible Euler, we know that they develop singularities. We know that those models, once they develop singularities, they probably become less relevant. But on the other hand, we know that Newton's laws do not develop singularities. Newton's laws exist for all time. So once your fluid model starts to develop singularities, you have to start going back to the more fundamental models, either the Boltzmann model or the particle model, okay? So I view this as a modern motivation for Hilbert's sixth problem. Hilbert said that his motivation was the rigorous foundations of geometry. Perhaps this is a more modern motivation for Hilbert's sixth problem, is to really understand what are the right models and what happens and how can we fix our models after the fluid singularity forms, okay? Again, this is a very interesting direction that is still understudied. Okay, so this is all. I'll stop here. Thank you.